Hello everyone, and thanks for being here, and also thanks to the organizer for having me. I'm sorry about not being there today. I left here some of my contacts, so if you have any question about the presentation, please contact me and I will answer it. Today I'm going to talk to you about our last work where we investigated the Afar volcanism by means of cluster analysis. So the first question is, why cluster analysis? Well, the main reason is the ever-growing number of analyzed samples available in online repository like Chem or geoch, and the fact that each one of these analyzed samples contains multiple elemental and isotopic analysis, which can vary independently due to the different geological processes. And this can make the interpretation of large datasets quite challenging. And also, traditional approach often relies on visual interpretation of a priori distinct samples based on their age or on their location, which can also introduce some bias. So unsupervised cluster analysis overcome these issues by statistically group samples of large multivariate dataset together without any a priori distinction of the samples. The other question is, why Afar? Well, Afar is a rift-rift type of junction. It's located at the intersection of Red Sea, Gulf of Aden, and the main Ethiopian rift. It's now guided by the divergent motion of Somalia, Arabia, and Nubia plates, and it starts forming around 30 million years ago after the arrival of the mantle plume, which is currently located in central Afar, around the Lake Abe. The current magmatic activity is dominated by the magmatic segment, the one that you see in blue here and depicted by this cartoon here in the middle. Magmatic segment which are marking the transition from the initial continental rift stage and the oceanic spreading stage, exemplified by the Red Sea. Magmatic segment which are also marking the shift from a plume-dominated source during the continental rift, here represented by the gray area of the Ethiopian flood basalt, and the MORB mantle source of the oceanic spreading, here represented by the Red Sea. And the magmatic segment and the Afar volcanism in general range between these two, and remember, and how this magmatic transition from plume to MORB occur is one of the main topics of this work. But let's go to take a closer look within Afar, and we can see that beside the older Dala and Mabra product outcropping at the margin of the depression, the Afar is dominated by the stratoids. We have the lowest stratoids in southern Afar, older than 2.5 million years, and the upper stratoids in central Afar, younger than 2.5 million years. Then we have the so-called Afar Gulf, which are associated to be the first magmatic activity, to be related to the formation of the magmatic segment, and then we have the actual ongoing activity of the magmatic segments, so the actual volcanism in red. Geophysical and petrological studies suggest that in the last broadly 5 million years, the rift moved from south to central Afar, where it then began to form the central Afar magmatic segment, which is the Mandararo magmatic segment here. Magmatic segment, besides being all characterized by the fact that they all have ongoing volcanic activity, they show some differences. For example, the persistent volcanic activity and thinner crust observed at the Ertale magmatic segment indicate that northern Afar is the most mature portion of the rift, so the one that is more close to the oceanization stage. So the aim of this work is to reveal how and when the mantle source, and in particular the plume component of the mantle source, changed during the rift evolution and during the continental breakup that is currently going on in Afar. To do that, we downloaded more than 1,000 data samples from geoch, and we perform 3 tests. Test 1 on major element, which was mainly carried out to evaluate the ability of the cluster to detect previously recognized group of samples. Test 2, which is a selection of trace elements, and it aimed to investigate variation in the mantle source. In this case, to get the best results from this test, we selected the input features by removing trace elements ratio that were highly correlated among each other. And we did that by carrying out the Pearson correlation coefficient. Lastly, in the third test, we used a selection of isotopic ratio to investigate the mantle source involved during the partial melting. For all the tests, the dataset of each test was standardized using the z-score. And also, since for test 1 major element are a constrained dataset that adds up to 100%, we apply a logarithmic ratio transformation, which allows basically to unconstrain the dataset. The results of all tests, so transform and not transform, are overall consistent among each other, but the best results are the non-transformed one. So these are the one that I will present here today. For all three tests, we perform both k-means and hierarchical clustering. Hierarchical basically builds a cluster by progressively merging the closest data points of cluster, as you can see from this picture here, while k-means starts from a predefined number of centroids and assign the data points to the closest of these centroids. It then recalculates the centroid position based on the new cluster points, and it continues to do this process until the centroid position do not longer change significantly. In both cases, we made the cluster range from 2 to 10, and to select the best number of cluster, we compare the results of the two clustering methods using the dissimilarity coefficient, which basically measures the overlap between the two clusters. Lastly, we perform the principal component analysis to reduce the dimensionality of the dataset and assess the separation of the identified cluster and also evaluate the goodness of the cluster itself. So let's move to the results. Here we have the results of test 1 on major element, where the best number of cluster identified is 7. Nearly all the clusters are distinct based on their degree of evolution, and in particular based on a fractional crystallization trend depicted in this graph here of the principal component analysis by this black arrow. However, at the same time, two groups of samples previously recognized in literature were identified by the clustering outside the fractional crystallization trend. One is a group of pantelleritic rock, and the other is a group characterized by plagioclase accumulation. But besides the specific, what test 1 is saying is that cluster analysis effectively identify different magmatic processes simultaneously. So we move to the test 2, where the best number of clusters is again 7. Some of these clusters, besides the fact that are being recognized in literature, are not discussed here due to their limited spatial distribution respect to the more, let's say, regional scale of this study. So here we will focus mainly on this three main mafic cluster. Cluster number 5, grouping mainly Ertaale and Alid in northern Afar. Cluster number 3, which basically group the upper strata is in central Afar, so the blue one. And cluster number 2, which group together the lower strata is in southern Afar here, together with the Mandararo magmatic segment and Azal magmatic segment in central Afar. But let's go to take a closer look to this three group, and we do it with this graph here, where we wanted to evaluate the presence of some minerals in the mantle source that can give us information about the mantle source itself. For example, dysprosium on ytterbium, which is a proxy of the depth of melting, and this is because ytterbium, which is an heavy rare earth element, is highly compatible in the garnet, which is stable in the deeper portion of the mantle. So if we melt the deeper portion of the mantle, the garnet is stable and the ytterbium will be retained in the garnet, and this ratio here will therefore increase. Otherwise, if we melt the shallower portion of the mantle, the garnet is not stable, the ytterbium is free to go into the melt, and this ratio will decrease. So based on this observation, we suggest a deeper melting column for the upper strata with respect to the rest of Afar. On the epsilon axis, we have instead dysprosium on dysprosium, which is sensible to residual amphibole and clinopyroxene in the mantle source, which are indicative of lithospheric metasomatic processes. Dysprosium is a middle rare earth element and is compatible in both clinopyroxene and amphibole. And this ratio here is basically the measured dysprosium on the dysprosium, which is calculated by the interpolation of the light rare earth element and the heavy rare earth element. So basically this ratio here indicates the deviation from the analyzed dysprosium with respect to what we expect from the rare earth element trend. So as before, if the amphibole and clinopyroxene are present in the lithosphere, so if there is metasomatism, dysprosium will be retained in this mineral and this ratio will decrease. Otherwise, if these minerals are not present, this dysprosium is free to go into the melt, and this ratio will increase. So with this in mind, we observe that there is a variation in dysprosium and dysprosium for all three clusters. So this suggests a diffuse metasomatism throughout Afar. But most importantly, we observe an increase of residual amphibole and clinopyroxene in cluster number 5, so in the northern Afar sample, which suggests an increase in contribution of the metasomatized lithosphere during the partial melting. So we now move to the last test, where the best number of cluster is 5, some of which again are not discussed, like these two, which is a small group of samples subject to cluster contamination, and we focus instead on these two clusters here. Cluster number 4, which again grouped together Alid and Erthale in northern Afar, this time together with some of the sample of Mandahinakir segment in central Afar, while cluster number 1 is basically, as you can see, the rest of the Afar samples. So let's go again to take a closer look to these two main groups. Here we have the classical isotopic graph, so lead 2006 versus 2007, lead 2006 versus lead 2008, and here instead we have strontium versus neodymium. On the right we have the zoom of these boxes here, and in here we have also the main mantle and member used in Afar, so the Afar plume, the Pan-African lithosphere, and the classical depleted Moore mantle. Overall, the sample as suggested in literature are a mix between these three and member, but we saw a clear distinction between the two groups. In particular, in the lead isotope, we can observe that cluster number 4, so northern Afar and part of the Mandahinakir, have higher lead isotope, all of them, so 2006, 7, and 8, which can be explained by an increase of the Afar plume or an increase of the Pan-African lithosphere. However, in the strontium versus neodymium graph, we observe no distinction between the two clusters, which suggests that there is no significant variation in the Pan-African lithosphere component during the partial melting, and therefore we suggest that this variation in the lead is due to a greater contribution of the Afar plume in the northern Afar. So now, how to fit all this observation in the rift evolution in Afar? As I suggested at the beginning, northern Afar is the most mature portion of the depression, not only with respect to the older product, but also with respect to the other magmatic segment. It represents the very last stage of the continental breakup, so how to explain the increase in the metasome component, but most importantly, in the plume component. But to do that, we suggest a focusing of the plume material beneath the already thin lithosphere of northern Afar, which enhance the formation of metasome within the lithosphere. Subsequently, the melting of this easy fusible metasomatized lithosphere further thin the lithosphere itself, and this allow the plume material to rise and to melt by decompression. So this mechanism here can explain the observed increase in both plume and metasome component that we observe in northern Afar. So to conclude, we show that cluster analysis enhance traditional geochemistry approach by identifying a group of samples already recognized in literature as well as revealing new one. We show an increasing contribution of the metasomatized lithosphere in northern Afar, associated with an increased contribution of the plume component at the most advanced stage of the Afar rift. And this, on a more broad scale, can suggest that rift evolution does not always trend towards a morb-like composition, but instead the plume-like signature can intensify even at the last stage of the continental breakup. And this is everything, and I'll thank you for your attention. If you have any question, please feel free to contact me. Thanks to everybody.